Okay, so our topic is about work. Work is the energy transferred by force. If you are applying a force on an object, if you are pulling it or pushing it, you're actually transferring the energy. Okay, transfer. There's energy that is transferred by the force you apply on the box. So energy transferred by force. The definition, work is also the product of force and the displacement along the direction of the force. So the mathematical equation, the definition, work is equal to force times displacement. So the equation is W is equal to F times S. The unit for work is Newton meter because force is in Newton and displacement is in meter. So 1 Newton meter is equal to 1 joule. The unit for work is Newton meter or joule. Joule is we use the capital letter J to as a symbol for joule. Now, work is done if the following conditions are present. So there is work done on an object if the following conditions are present. One is if there is a force applied, and number two, if the displacement is in the same direction as the force. Right? Look at this figure here, this illustration. So the displacement is to the right. The box is being pulled to the right, and the force is also to the right. It's pulled to the right. So both force and displacement are in the same direction. So the formula W is equal to Fs holds true only if the force acts in the same direction as the displacement. So to solve for the work done on the object, its work is equal to force times displacement, or Fs. How about if the force is not in the same direction as the displacement? Okay, if the force is not in the same direction as the displacement, or not in the same direction as the motion of the object, you get the component of the force which is in the same direction as the displacement. And then you multiply that with the s, or displacement. Get the f of x if the displacement is in the x direction, and f of y if the displacement is in the y direction. Okay, there we have an example here. So the force is applied at an angle theta. So it's not up or downward to the right or to the left. It is to the right at a certain angle. So it's someone is pulling this box at a certain angle theta. Since the S and the F are not in the same direction, how what are we going to do to solve the work done by the force? So remember that force is a vector and it has x and y components. So its x is in this direction and the y component is in this direction. Okay, so the x component is the component of the force that is in the x direction. So f of x, we can get f of x. Let's get the f of x and then multiply that by the displacement. So they are both in the x direction. So remember that work is force times s. So the x component of force that is in the x direction times the displacement, which is also the x direction to the right. Now we use the cosine function to get the magnitude of our f of x. How much is f of x? And then multiply that with the s. Okay, for this, you can use the cosine function. Cosine theta is equal to the uh, adjacent side. Adjacent side to theta is the f of x. So adjacent to this angle is the f of x. This side, and then divide that with the hypotenuse, which is the f. This is our hypotenuse, the longest side of the triangle. So we're f. Okay, and then when you get rid of f of x, you multiply the force by the cosine of theta. Then substitute that here. F of x is f cosine theta, and then you multiply that with displacement, and you get work is equal to fs cosine theta. So if force is applied at a certain angle, the formula for work is fs cosine of theta. Okay, and if it is If both the force and displacement are in the same direction, you use F is equal to Fs. Okay, now let's discuss that further here. So for this, if you're given this, if the force is at a certain angle, always remember SOHCAHTOA. You can use the SOHCAHTOA, and you can choose the applicable function to use in the problem. So let's discuss that further. Okay, so here you have the force. The hypotenuse is the force, and the x component is f of x, and the y component is f sub x, and the y component is f sub y. Now this side f sub y is opposite to your theta, and f of x is adjacent to theta. That means the f of x side, this side, is next to, it's next to theta or adjacent to theta. Okay, but f of y is opposite. Now, SOHCAHTOA, which one is applicable in this situation in order to get the work done on an object? So out of these three, Ka is the most applicable. So adjacent side fx divided by the hypotenuse f. So adjacent over hypotenuse. So cosine of theta is equal to f sub x over force. So to get the f of x, and to get the f sub x, or the fx, you multiply cosine of theta by force. So that gives you f cosine theta. Work is f of x times displacement, f sub x times displacement. So substitute f cosine theta into this equation, into this quantity, and then you multiply f cosine theta by the displacement, and you get the final formula for work, and that is Fs cosine of theta. Okay. So we have discussed about the SOHCAHTOA previously. So in the previous chapter, we discussed SOHCAHTOA. So I'm sure you are all familiar with the SOHCAHTOA. How about if we have this, we have a box and there are three forces acting on this object. So how are we going to get the work done by F1, F2, and F3? This one is upward, okay? And the F3 is acting in the opposite direction of the displacement, while F is applied at a certain angle. Someone is pulling this box at a certain angle. Okay, so how are we going to solve for the work done by F1, F2, F3? And then if we're going to add the total work done by all these three, we'll get the total work done. So how are we going to get the total work done by the three forces on this object? Okay. So of course for F1, you just get the x component, which is in the same direction of the displacement. And then you solve for F2 and F3, you add all the work done by these three forces and you get the total. Okay, so like this. So F1 work by F1, work by F2, work by F3, and then you add all the vector sum of all the work done on this object. Okay, how are we going to do that? Okay, before we solve this, let's discuss the different cases. Okay, so if you want to solve that kind of problem, you need to consider the different cases. Like for example, if your force is in the same direction as the displacement, the formula you're going to use is Fs. W is equal to Fs. How did we get that? The derivation. What is the derivation of this equation? So always consider the angle theta between the force and the displacement. So here, the theta between force and displacement is 0. So using the formula Fs cosine of theta, okay, cosine of theta is equal to 1. So 1 times S times F equals Fs. So that is why the formula for work is force times S, because in this situation, theta is 0. How about in case 2, if you have, okay, before we discuss case 2, you see work is equal to Fs. There is positive work done in this situation, in this case. Okay, if they are in the same direction, there is positive work done on the object. Now, case 2, how about if you're given the situation where the force is perpendicular or 90 degrees to the displacement? This one is to the right, this one is upwards. So 90 degrees. So work is equal to Fs cosine theta. We know that cosine theta is 0. So 0 times Fs is 0. So if the force is perpendicular to the displacement, there is 0 work done on the object. That means there is no work done in the object. Okay. Now, one example of this is, so when I say that work is done, okay, imagine you are lifting a box. You are lifting the box from the floor. So your palm, the palm of your hand is pushing the box upward. So you can lift it upwards. Okay. The force of your palm is upwards. So the applied force is upwards. You apply an upward force to the box. And then the displacement is also upwards. So since you are lifting the box from the floor, so the displacement is upwards. That means the force on the box and the displacement are in the same direction. So we say that when you lift the box, there's work done. Okay? Because the theta between the force and the displacement upwards is equal to 0. So cosine of 0 is 1. So work is F times S, positive work done. How about if you start walking after lifting the box? When you start walking and you move to the right, the displacement of the box is to the right, but the force is upwards. So your palm is applying a force to the box. In the direction of the force is upwards, but the box is moving to the right because we're walking to the right. Since the displacement is to the right and the force is upward, that means that the angle or theta between F and S is 90 degrees. So when you start walking, there is no work done. When you lift the box, there is work done. So in physics, there's no work done. Even if you are walking for 10 minutes and you're lifting this or carrying this heavy box for 10 minutes. So it's a huge box, heavy box, and you walk for 10 minutes to the right. However tired you are, you can still say that there is no work done. You did not do any work to the box, to the object. No work done. No work was done on the object because your force and your displacement are perpendicular to each other. Okay, so by definition in physics, no work done, however tired you are. Okay, let's make that clear. So there's no work done. How about in case 3, if you have this case 3? Case 3, the displacement of the box is to the right. And as you pull the object to the right, and as the box moves to the right, there is an F pulling it in opposite direction. So there is a resistive force that is acting in the opposite direction. So while someone is pulling it to the right, a resistive force is pulling it to the left, slowing it down, making it difficult uh, to move the object to the right. So if this is the case, the theta or angle between them is 180 degrees. Okay, and we know that cosine of 180 is -1. So therefore, work Fs cosine theta, the work done is negative Fs. So here in this situation, there is negative work done. So let's review case 1, same direction, there's positive work done. Okay, second situation, force and displacement are perpendicular to each other. There's no work done. In this case, opposite direction, there is work done, but it's a negative work. There's negative work done in this situation, on this object. Okay, now how about case 4? In case 4, the force is applied at a certain angle, theta, and it's not in the same direction as the displacement. So remember, we discussed this before, okay? If the theta is greater than 1 but less than 180, that means the theta should be from 1 degrees to 179, except, of course, 0 and 90. Now, you get the component of the force that is in the same direction as the displacement. Since the displacement is in the x direction, to the right, we get the x component of force. So this disregard the y component here. So then f of x, multiply that by s. So f times s, and then the cosine of theta. So there's positive work done here. Okay, case 4. Now, how are we going? Let's go back to that problem. How are we going to solve for this problem? This one. Now, this one is F1. This is case 4, right? And F2 is case 2. And F3 is case 3. Okay? Let's review. Let's review. Summarize. Let's summarize that again. So theta, if the angle is equal to 0, then work is Fs. There is positive work done on the object. If theta is 90 degrees, then work is equal to 0 joules. No work done. If theta is 180, work done is negative. The work done is negative F times S. There's negative work done in this situation. And case 4, number 4, if the theta is greater than 1 but less than 180, there's positive work done. And the formula is W is equal to Fs, cosine of theta. Okay, here F times S, here negative Fs, 0. And here case 4, okay, let's write the formula for case 4. Here you have work is equal to F, okay, this is a vector, so F cosine of theta times S. Okay, I forgot the S here. Okay, so this should be Fs here. Fs cosine of theta. Okay, let's write that again. F and then S. So vector displacement, then cosine of theta. So that's the formula for work case 4. Now let's clear that up. Okay, let's erase and then okay, let's go back. How are we going to solve this problem now? We're going to apply those 4 cases. Okay, we're going to get for the total work done. Okay, this one. Okay, so F2, 90 degrees to the displacement. That means the answer here is 0. Okay, let's write. Okay, the answer for F2 is 0. How about F3? F3 is opposite direction of S. So 180 degrees, right? So displacement to the right and F3 is to the left. So the angle between them is 180. And we know cosine of 180 is negative 1. So therefore, work is F, negative F times S. So let's have negative. And then what is F? F is, let's say, okay, not this one. Wait, it's the wrong one. Where is it? Let's solve that one. Let's solve that one. First example. Let's start with the first example here. Okay. Okay, in the first example here, let's clear all drawings. Okay, in this example, you have a force that is 200 Newton. Displacement to the right, 50 Newton. What's the work done here? So you have 20. Work is, this is case 1, right? So you just multiply F times S. So 200 times 50 is 10,000 Newton meter, or 10,000 joules. So let's write 10,000. So it's 10,000. So 10,000 Newton meter or joule. So Newton meter or joule. 10,000 joules. Okay, next. How about case 2? How about example 2? You have an example here. Okay, you have 80 newtons. The force is at an angle 60 degrees. And you have displacement 4 meters. So remember, this is the x component is f of x, f sub x, and multiply that by s. Okay, f sub x times s, or displacement. So let's multiply 80 newtons, multiply that by, of course, remember f of x is f cosine of theta. So f cosine theta. So cosine theta, what is cosine of 60? And then you multiply that with 4 meters. Then you have 4 meters. So remember that cosine of 60 is 1/2. So this is 1/2. 1/2 of 80 is 40. So this is 40 times 4 meters. Okay. So the answer is 160. 160. It's 160 joules. 160 Newton meter, or 160 joules. Okay. It's clear. Okay, next example. How about if this one, we're given this one. How are we going to solve for the total work done on this object? There are 3 forces acting on this object, F1, F2, F3. So to get the total work done, to get the work done by F1, work done by F2, and work done by F3. And then you add the vector sum of 3, and that is the total work done, or the sigma work. Okay, so F2. F2 is 90 degrees perpendicular to the displacement. Therefore, here the work done is 0. So let's write 0 here. 0 work done. Now, F3 is in opposite direction. Okay, opposite direction with the displacement. So the angle between them is 180 degrees. And we know that cosine of 180 is -1. Right? So cosine of 180 is -1. This is case 3, right? This is case 3, where F is equal to, our work is equal to F cosine of theta. So F cosine of theta, F is 5. So F is 5. Since F is 5, we multiply that with the cosine of 180. Cosine of 180 is Fs. So F is 5, S is also 5. So multiply that by 5. So 5 newtons times 5 meters. Then multiply that by the cosine of 180. Cosine of 180 is -1. So -1. That means here the work done is 25. Here you have 25. So let's clear that. Here you have 25 joules, but it's negative work. Negative 25 joules. The negative came from cosine 180, which is -1. Okay, and then here 0. How about F1? So F1, case 4, Fs cosine of theta. So F is 18. So let's write 18. Here, 18. And then Fs. So S is 5 meters. So multiply this with work is Fs multiplied by S, which is 5. Okay, and then cosine of, multiplied by the cosine of, multiply this by the cosine of 60. Okay. So what is cosine of 60? Remember that cosine of 60 is 1/2. Okay, so it's 1/2 here. So what's the answer? 18 times 5. So what is 18 times 5? Okay. So what is 18 times 5? 18 times 5 is 90. Right? 90. And then multiply that by 1/2. So 1/2 of 90 is 45. So 1/2 of 90 is 45. So there's positive work done there, 45 joules. So 45 joules plus 0 minus 25 is equal to 20. Positive work, 20 joules of work. So a total of 20 joules of work is done on these objects, okay? Okay, next. Total work done on the object is 20 joules. Next, let's clear everything. Okay, next. A constant horizontal force of 400 Newton is required to drag the box across a rough surface at a distance of 50 meters. How much work is done, or how much work is needed to do this? So case 1, same direction. So 400 times 50 is 20,000 joules of work. Okay, the answer is 20,000, 400 times 50. How about the next one? Next problem. How about this one? A box was pulled along a handle with a force of 80 newtons. If the handle made an angle theta of 60 degrees to the direction of motion, and the box moved through a distance of 4 meters, how much is the total work done by the force? Okay, so the theta is 53 degrees. Let's change this 60 degrees to 53 degrees. So how are we going to solve this? Okay, remember this is case 4, Fs cosine of theta. What is F? F is 80. Fs cosine of theta. So 80 is the F, S is 4 meters. So multiply this with 4 meters. So 80 times 4. And then cosine of 53. What is cosine of 53? Okay. Cosine of 53 is 3 over 5. So this is 3 over 5. Okay, let's check the most commonly used theta or angle. Okay, here we have the most commonly used angle: 30 degrees, 60 degrees, 53 degrees, 37 degrees. So you must remember this. Sine 30 is 1/2. Cosine 30 is square root of 3 over 2. Sine 60 is square root of 3 over 2. Cosine 60, 1/2. Cosine of 53 is 3 over 5. Sine 37 is also 3 over 5. While sine 53 is 4 over 5. And cosine 37 is also 4 over 5. Okay? You must remember this 8. Okay? Because these are most commonly used, the most commonly used in problems, physics problems. So let's go back to that problem. Okay, let's solve for the work done. Okay, so if this is 3 over 5, then this is 320 times 3 over 5. So you multiply this by, so times 3 over 5. So the answer is, here you have, the answer is 192 joules. If you're going to solve it, the answer is 192 joules. Okay, 192 joules. Okay, 320 times 3 and then divided by 5 is 192. Okay, let's save that. Then clear. Let's go to the next problem. Okay,